Let us look at the thorium lead method. Here 232 thorium alters to 208 lead, and this involves alpha decay, which is 2He4. So, here this is the parent and that is the daughter. So, how to write the equation? 208 Pb the daughter plus 208 Pb at some time plus 232 Th, which is the parent, multiplied by e to the power lambda 232 T and then minus 1. Here the stable isotope that is used in the equation is 204 Pb. Now, let us take the uranium lead method of dating. Here 235 U is decayed to 207 Pb or lead. So, how the equation will be constructed? Parent goes to the daughter, 207 Pb is written here, 207 Pb initial T and plus 235 U is written here, multiplied by e to the power lambda 235 T minus 1. Here also we involve a division by a stable isotope 204 Pb. So, out of these methods I have stated 1, 2, 3, 4, 5 and 6. There are two radioactive decay, namely the thorium lead and uranium lead, where the stable isotope 204 Pb is used in the equation. In mass spectrometer, we can undertake the dating process. These ratios are obtained, lambda is known and therefore T is found out. What I said just now regarding equation 6, same thing for equations 1 to 5 hold true. Regarding uranium lead dating, we have to remember that isotopes of uranium are all unstable and decays to daughter elements, which includes thorium, radon and lead. These are the three transformations. 238U to 206 Pb has a half-life of 4.47 billion years. Dating of zircon has been used to establish the age of the oldest rocks in the world, where the uranium lead dating was applied. This equation can be written in a more general form as R equal to R0 plus R P slash D e to the power lambda T minus 1, where R0 is the initial ratio and Rp slash D is the parent daughter ratio at time t. This equation is known as the isochron equation. There are certain radioactive decay such as potassium argon and ReOS, where R0 can be neglected because it is too small, or if R is much more than R0, the equation can be simplified to R equal to Rp slash D multiplied by e to the power lambda T minus 1. Now, R and Rp by D can be measured from two samples, and then if I subtract two such equations one from another, then we get delta R equal to delta Rp slash D e to the power lambda T minus 1. Now, from here we can write delta R divided by delta Rp slash D is equal to e to the power lambda T minus 1. Obviously, T is given this form, and for a given value of T, this is the equation of a straight line. So, if we plot R versus Rp slash D, we get a straight line, and that line is known as an isochron. This straight line is known as an isochron. While several decay constants were presented, note that the decay constants for Rb, La and Lu and Re are less well known and continue to be active research topics. Let us look at the potassium argon calcium system. This system is little bit different from what has been discussed so far. 40 K alters to 40 Ar. There is in fact a branch decay. 40 K nucleus may decay to either 40 Ca by a beta decay or to 40 A by electron capture. Potassium can give radioactive decay and produce argon, it can also produce calcium. Now, it is impossible to the present state of knowledge to predict how a particular 40 K atom will decay, just as it is impossible to predict when it will decay. Therefore, to present the situation, we define the branching ratio RB equal to lambda EC divided by lambda beta, where lambda EC is the decay constant related to the electron capture, E for electron, C for capture, that is why the subscript is written, and it is for potassium to argon decay, and lambda B is the decay constant for potassium to calcium radioactive decay. So, the two decay constants are used to define a branching ratio RB, and as per a 2010 publication, this branching ratio RB for potassium argon calcium system is 0.1037, and the lambda EC and the lambda beta values are presented here. The total decay constant may be useful for 40 K, and this is given by lambda is equal to, instead of division we add up lambda beta plus lambda EC, and it is 5.5492 multiplied by 10 to the power minus 10 per year. RB is unitless because it is divided by the same kind of parameter, whereas the total decay constant certainly has a unit and it is per year. Recollect this equation, d star equal to n multiplied by e to the power lambda t minus 1. So, in case of the potassium to argon radioactive decay, d star becomes 40 AR, which is here stated as 40 AR star, and then e to the power lambda t minus 1 is placed here, n becomes, and here is a different form, lambda e by lambda multiplied by 40 K, where lambda is the total decay constant given here, and lambda E is the lambda EC. Recollect, lambda EC is the decay constant related to potassium to argon transformation and the related electron capture. Similar to this equation, one can also write an equation for 40 K to calcium transformation, and it will be given by 40 Ca is equal to lambda beta divided by lambda 40 K multiplied by e to the power lambda t minus 1. That is what is said here. We can write a similar equation for 40 Ca star in this way. The star that is used means that radiogenic 40 AR, this star, and if I put a star, this means a radiogenic calcium. Now, although we have said that from potassium to argon transformation is possible and potassium to calcium transformation is possible, most of the research, but not all the research, has focused on potassium argon transformation. The reason is 40 K by 40 Ca for the reaction K to Ca transformation is usually very small. 40 K is least abundant and 40 Ca is very abundant. So, as a result, the ratio 40 K by 40 Ca becomes very small. It is so small that it becomes difficult to detect or difficult to measure. Radioactive decay, potassium alters to argon or argon goes to argon, and this daughter argon, if the rock or the material is deformed, can be lost. So, if we date the deformed rock, we may get age of deformation, not the age of the rock. This is a general statement and one can see in more detail if he is interested. Now, even this equation may not be sufficient to date the rock based on potassium argon dating technique. The reason is there can be already atmospheric argon present within the sample. So, we need to make a correction of equation 2.41, and here is the correction. 296.2 is added here because in the atmosphere 40 air by 36 air ratio is 296.16. So, this is the atmospheric correction, rest of the thing are same. And one more thing, then equation 2.41 is everywhere we have divided by 36 AR. We have not done the division here, why? Because already the division is made. Potassium argon is a widely used method of dating orthogenic minerals such as glauconites and volcanic rocks, lavas and tuffs that contain potassium in minerals such as some feldspats and micas. Uranium-led dating method is used to date very old rocks such as the Archean rocks, meteorites. Let us look at the 40 AR 39 AR dating technique, but briefly. This is a highly accurate radiometric method for determining the age of geological materials, volcanic rocks and associated fossils from millions to billions of years old. And in this case, here is the final equation. More difficult and expensive method, argon-argon dating technique, is now preferred to potassium argon dating. By step heating, one finds out the 39 AR and 40 AR present using mass spectrometer. To find the isotopic ratios at different temperatures, the sample is heated until there is no change in ratio with increasing temperature and plateau is reached. If the plateau is not reached, then we will exclude such samples because they can't give the reliable date. Let us take an example of isochron in the RBSR dating method. 87 RB by 86 SR is plotted along the x axis and 87 SR by 86 SR is plotted along the y axis. From the sample, different points have been obtained and a straight line best fit has been given. This line is known as the isochron in case of the RBSR dating. Similarly, the other isochrons can be defined for the other dating techniques. We will look at the C14 dating principles. This can be performed on wood, peat, charcoal, bone, leaves and CaCO3 shells of marine organisms. Whenever there is carbon available and also in the CaCO3 shells of marine organisms, this dating can be applied. Extensively it has been used to estimate ages of archaeological materials. If an old civilization is to be dated, say the Harappan civilization, carbon 14 method can be performed not just in geology, therefore in archaeology it has its use. In geology, its use is limited to the quaternary geology, to the quaternary period. The C14 is produced in the atmosphere owing to the impact of cosmic ray neutrons on ordinary nitrogen 14 atoms. On N14, there are effects of cosmic ray neutrons and it produces 14 carbon. This 14 carbon is incorporated in carbon dioxide. Now, this carbon dioxide is assimilated by plants and animals during their life cycle. This CO2 is taken up by plants during photosynthesis and the animals which eat plants progressively in their body 14C goes inside. When plants and animals die, their tissues no longer assimilate new radioactive carbon. Thus, the amount of radiocarbon in the organisms start diminishing with time. The age of a sample is determined by measuring the amount of radiocarbon per gram of total carbon in a sample and comparing this amount with the initial amount at the time of organism died. The age equation is T equal to 19.035 multiplied by 10 cube log A0 by A years. So many years would be the time. A is the measured activity of the sample at the present moment, at present, and it is given by the unit is disintegrations per minute per gram of carbon, disintegration per minute per gram of carbon, and A0 is the initial activity. Note, we have used here LOG log, which means it is log to the base 10, and A0 by A, since similar kind of parameter, so it is unitless. There are two kinds of modification in the radioactive carbon in the atmosphere. There are two counteracting processes. One is the burning of trees and fossil fuels in the past few centuries. This has produced a relative decrease in the relative carbon in the atmosphere, but thermonuclear bombs and their use has slightly created an increase. Therefore, corrections must be made for these changes to obtain correct radiocarbon ages. So, the equation which is written here, some corrections are also added. The C14 dating technique is restricted for materials of less than about 40,000 years old, which means if we want to date a meteorite which is billion year old, uranium lead method might work, but not the C14 dating. By special technique, rocks or materials as old as 60,000 to 80,000 years has also been possible to date. Efficiently, C14 dating can be used to estimate ages of very young sediments in cores of deep sea sediments and to find out the glacial history by analysis of wood in the glacial deposits. Within glacial deposits, wood can be found, recent glacial materials, and there the wood can be dated. Now, since C14 is of extremely short range, last maybe 50,000 to 70,000 years, the method is of little value in calibrating the geological time scale except for the recent quaternary events. Only in recent quaternary events C14 is useful to divide the geological time scale and get the ages, but considering the overall geological time scale 4.6 billion year till the present, C14 in that context its use is limited. How an indirect approach of dating can be performed? Consider here is a batholith of age around 135 million year and it is obtained by geochronologic process. There is an unconformity, then there are sedimentary layers, and these sediments and the batholith, everything is cut by a dike of 125 million year. So, what can we conclude? We can say that these sediments are of age which is less than 135 million year because it is lying over the 135 million year old batholith, and is more than 125 million year. Why we are saying? Because of the cross cut relationship. Take another case where below an unconformity regional metamorphosed sedimentary rock has been dated with the age of 100 million year. Then there are sedimentary records, and over that here is a seal and it is dated to be 80 million years. This means the material which is here is younger than 100 million year, so less than 100 million year, and since a seal has been identified, we can say that this range of sedimentary rocks are aged more than 80 million years. So, all in all, this sedimentary package or the rock package is having an age which is less than 100 million year and it goes to more than 80 million year. This is the indirect approach of understanding the date without dating exactly the rock, but after dating the dike that cuts it or the rock which is at the bottom or which is at the top. The problem of radiometric dating in stratigraphy is that it can have its limited use because not every lithology can be dated as per our wish. Problem of precision is also another issue. With older rocks, this becomes more important. For example, if two lava beds were formed only with a million year apart and there is a margin of error in the dating method of 1 million year itself, then correlation becomes problematic. There are several geochronologic dates available from the Indian peninsula and from the country India. I am going to refer only one as an example. The geohistorical significance changed along with this date. This is Mumbai, from where I am recording this NPTEL lecture. South of the Deccan Trap and south of Goa is a village Malpe coming within the Udupi district. If one moves to the Arabian Sea from Malpe, one comes across a St. Mary's Island. Here is a detail of the island. One of the big islands is the Coconut Island. The rock type in this place, in these islands, are the felsic volcanics, rhyolites and rhyodicites. It was originally considered to be an offshoot or a product of around 65 million year old Deccan volcanic province. This is the main exposure of the Deccan Trap. The Deccan Trap and the St. Mary Islands do not have a connection in between in terms of rocks, rather there is Arabian Sea. Now, when the dating was done by 40 AR 39 AR method on the St. Mary's Islands rocks SMI, it yielded an age of 85.6 plus minus 0.9 million year. This age is significantly different from the Deccan volcanic province's age, which is around 65 million year. So, the interpretation of Indian tectonics changed significantly. This age comes close to the Madagascar flat basalt province's ages. Madagascar is here and this microplate is presently far away from the Indian mainland, and the age of 85.6 plus minus 0.9 million year also comes close to the Kerala dikes. This is the Indian state Kerala. Some of the dikes here are of this age. So, here goes the interpretation. The Madagascar flat basalt province, which is within the Madagascar microplate, the SMI volcanics, which is in the St. Mary's Island, and possibly the Kerala dikes, which are all these three locations are far away from each other. They represent volcanic activity associated with the breakup of Greater India and Madagascar. Greater India at that moment was consisting of the present day India and the Seychelles Islands, which is now not shown in this map. Seychelles was attached with Saurashtra and that got separated around 65 million year back. So, the Greater India consisting of India and Seychelles separated from Madagascar, and that happened in the Upper Cretaceous around 88 million year back. Possibly due to the India-Madagascar separation, during this separation time, the volcanism was a manifestation in terms of the SMI rocks. So, in this way, the interpretation changed significantly with the availability of reliable geochronologic information.